Start recording.
Okay, thank you.
Yeah, let's start recording from here.
Okay, thank you. Bye.
Wow.
Okay, boom, so there it is. So we have our equation here. Just want to make sure we write it right.
Just put me back to class.
He said he won't make it to this class, so he'll make it to the other classes. Yeah.
About a day later.
Yeah, not
So it'll feel crappy tomorrow.
Yeah.
Okay, part two. Part two. Let's go with part two. Still back to this guy here.
Yes, definitely.
And so we're still looking at the the integral from 0 to whatever.
From 0 to x.
0 to x, of x dx, right? And we know now it's 1/2 x squared. That's cool.
What? Wait, did you start recording?
Yeah, start recording. So let's go to part two. Still going to do the same function since we're with it here. So everybody agreed that is true? That's cool. So then if I do want to go to, oh, hold on. So let's back up. So you guys said whenever we went to like 1 or to 2 or to 3, right? Notice what happened was, let's go to 3 as an example problem here. All we did is we plugged in that value, true? And that turned out to be 4.5. That's neat. So the question is this: what happens if you were to plug in a, oh, hold on, how about this? I'm going to cut this off. I'm going to go from 3, but I'm going to cut it off right here. So I actually just want to know the trapezoid, not that. I want to take this off right here. So I want to go from 1 to 3, x dx. We know the formula already, right? Formula is 1/2 x squared. That's the.
And we do like minus.
Yeah, you have to. Yeah, Eli's correct. You're taking off an area, right? And you have to take off area of 1, right? So see if this makes sense.
Oh, so you can split it, couldn't you?
And not so much splitting, but subtracting. See if this makes. So if we do this right here, right?
Yeah.
We're gonna have to.
Do minus 1/2 1 squared.
So it's as if you had done 0 to 3 minus 0 to 1. Right?
As if you were done 0 to 3.
Yeah.
Yeah, and then you did 1 to 3 subtracted.
But
0
then
to
how does
1.
that work with something that's
Bless
not?
you,
No,
Taylor.
opposite though. 1 to 3 equals 0 to 3 minus 0 to 1, right?
Yeah, 1 to 3 is 0 to 3 minus 1.
0 to 3.
And then the other one, yeah.
Cool. Or look at this, what we're doing. We're plugging in the 3 into here, and then we're subtracting off the stuff we don't need in front, right? We're plugging in that little 1
So you
after we've taken already the antiderivative. Are we good there? Let's see if it works on another form. Let's see. Let's do an easy one. Okay, does this make sense to you guys, first of all?
Yeah.
As far as areas are concerned, and all we're doing is we're taking off the extra.
Why? Just that we.
Because we only want the area from here to here. Okay? And so that means all I really got to do is I got to figure out what the antiderivative is, and I just plug in my endpoints, and I'm done. Let's see if that worked on another one that we did in 5.1. This is another part. Remember this one from Monday's class? We went from 2 to 5. I'm going to write it on top though. I want this area right here. And it was y is equal to 4. Good? So let's see. Hey, let's see if this works. So can you guys write it as an integral first? Actually, no, let's do it even easier. Give me the area of it real quick here. Area is 12. That's easy enough. Cool. Let's see if all this stuff makes sense, mathematical sense here. So now, can you write this as an integral? From where to where or what?
5,
2 to 5, perfect,
4 dx.
Yeah, 4, and it's dx. Okay, now, what's the antiderivative of 4? What if you take the derivative, it would make 4?
4x.
4x, right? Here's this is what we're going to work on right now in just a bit here. So if I have a 4x, the derivative of 4x is 4.
So it's literally just going backwards from the.
Absolutely. That's what the opposite operation is all about. Good.
Yeah, well, that seems like it can be kind of tricky though, because can't multiple formulas have the same derivative?
Oh, awesome. Yes. Okay, cool. So let's look at this here. 4x, let's say plus 5, right? If you take the derivative of this,
So
you're going to get 4, right? Or if I switch this to a 12, I'm still going to get 4. Interesting. We'll handle that in 5.4. That's for Monday, but good observation. Okay, so this little extra. Now, the question for us is, why don't we have the extra here? Let's say it's a 7, so we don't mess with our numbers here. So think about, why don't we have the extra thing here? We don't have to even think about it. But let's go this way. Let's finish this up. Everybody okay with 4x? And here's what we do. We say to ourselves, you know what? Here's it's called the evaluation bar. Sometimes it's written like this. Sometimes it has these little side like this. Kind of depends which book you're using. Let's see what is our book using. I think they use this one right here with this little. So you go 2 to 5. That's what you do. And let's plug in the 5. Let's subtract out the 2. Let's see if we get our 12 out of it. Yep. So we said this. We said that all we got to do is plug in the top
plug in
value.
20 and then subtract it from
8. And the question is, do we get our 12? Yes, that is so cool.
Oh, that makes sense.
Okay, but Tay, let's handle the your situation with the constant, so it's not too much of a mystery here. And then let's put the fundamental theorem of calculus together, and then we'll do the example problems. Cool. You guys are awesome. This is so enjoyable to go through this here. So first things first, this little c value, notice we get a constant. If we were to go backwards, we always get a constant if we do an antiderivative. Everybody agree there? Because the derivative would produce this guy to be a 0, right? So if I were just to go, let's do the same problem. Let's include the c as part of our answer. We good? So let's do the exact same problem. So we're going to go from 2 to 5, 4 dx. Good there, Christopher? So as we take the antiderivative, we're going to make ourselves a formula with c included as part of our answer. Are we good?
How can we find what c was? It always goes to 0.
Correct, yeah. And that's what 5.4 is all about. But just for us to sort of see it right here, notice what's going to happen here. If I were to plug in a 5 into the 4, I get this little c extra, right?
Yeah, so what would be the right answer?
Minus, I plug in
You're
the,
gonna subtract the c, so it doesn't really matter.
there it is. It doesn't, it disappears
That's
on
just
us.
this problem though, right?
No, but in all problems, if you have just a constant, it's gonna be added or subtracted. But then it'll
What
just
if
cancel
you
each other out
go
and you add it all
from-
together.
What if you don't have to do a subtraction?
Taya's being the student.
What if
I got my
you-
hand raised.
You're up to 3.
Uh-huh,
Then you
absolutely.
might have to do that, and then you have an extra constant that might or might not be there.
Perfect. Yep, good.
Okay, sorry, I know I'm causing a bunch of problems, but.
No, not at all.
This is with constants.
This is this,
But what if you have like, 2x, for example? Then it could be like 1/2 x to the 4th, or just x squared.
sure, for antiderivatives, even if you do powers of things, you're still gonna have just a constant afterwards, because it's just a constant that gets you to 0.
Yeah, but I mean, getting to the derivative,
Uh-huh.
like the derivative 2x could come from a couple different places. Even like like disregarding the constant. because, like,
Oh,
we
yeah,
have
go
different-
ahead. Show me. From where? Let's talk about it. Guys, this is it. This is a conversation to be had as opposed to just a lecture and then go on. So talk to me, what would be a problem that you would
Okay,
consider?
so say you have 2x as your graph, your line,
Uh-huh,
that could come from 1/2 x to the 4th, for example, or it could come from x to x squared.
That would go to 2x cubed.
yeah, this one,
Oh, yeah,
this,
that's true,
right?
that's true.
because you just only subtract one from the exponent, right? You don't, so this guy here, that would give you 2x cubed still, because you only subtract one from there.
But there are
I
other-
forgot about that.
Mhm. So this one give you the 2x. But so with rules, power rules, any other rules, yeah, you're only gonna have one answer.
Okay,
When you go backwards, you're just gonna have that. So if you had like this, that still gets you a 2.
Yeah.
If you had like this, still gets you the 2, right? But then if you add a, this is not a good example here. Let's go here, like this right here. That gets you 2x, right? That gets you a 2x. That gets you a 2x.
okay.
But then once you, no, this is, but once I do this, I just change it, right? Because now I have a plus 170 at the end for my derivative. So it's the constant that's the problem here. So
Are there other problems other than constants, other things that would cause problems?
no, discontinuity, which we'll talk about in just a bit here.
But that's a different issue.
Yeah, So it's the constant, it's the extra little piece there. The reason why we don't have to worry about it now is because notice we're plugging in a top end and we plug a bottom end, right?
And then they cross out.
And then the cancel. So what we do is we call this definite integrals. And so let's go back to the fundamental theorem of calculus. That's what we're covering. And we probably should put into here. Let me see if it's actually in here or not here. If it's not in here. But underneath the title for today, can you guys put in definite integrals? And Enrique put this in later. Definite integrals, which means we have a starting point and we have a stopping point. We're good? 5.4, just to get you prepped for Monday, says, what happens if we get rid of the limits altogether? I just want to know in
The
theory,
entire thing?
what is the entire thing?
And
Okay, that's
You
5.4.
couldn't do that though, if there were no limits.
Huh, we'll
It's stopped
see.
somewhere.
I don't know.
Uh,
Okay, let's write the fundamental theorem of calculus. Let's write it and then we'll practice it here. So F for short, how about this? FTC. Fundamental theorem of calculus. Why is it so important? Is because it brought these two things together. It brought the derivatives and integrals together into one piece and connected them. We're good? And now we have this conversation now. So here we go. Suppose F is continuous, and of course, on A to B. Oh, A to B. Okay, so fundamental theorem of calculus, here we go. There's two parts to it. Number one, if g of x is equal to this function, so a whole bunch of different variables here. So there's the connection between, come on, chicken scratch, let's go. Then there's a derivative relationship here established. That was part one. Part two,
F of F,
T?
F of T.
f of t. You got to use a different variable so then I can use x's later on. So t is our initial variable inside there. X is the variable I end up with later on. Just to show that my plug-in value for t is later on. Just like we plugged in the
Is that F of T?
f of t dt. So all it's saying is I used a variable, but after I use it, I'm going to plug in the x into the variable.
Yeah.
Okay, so then
It's just saying that f of t is the same thing as f of x if you're going to x.
yeah,
That's
So,
not really, do you have to prove that? Or isn't that just kind of the definition of functions.
Yeah, so yeah, in this case, what we use a different variable here, not to confuse it with the x that we plug in later on. Because you're saying f of t is some kind of arbitrary function in space,
Oh,
right? And we're gonna take the antiderivative of that, but eventually plug it at x into it.
Sorry, Mr. Montier, on the second part of G prime of X, are those both X's in the parentheses? Or is it F of T again?
X and x.
Okay,
Uh-huh.
thank you.
Yeah, because we plug in this little guy right here, this little top value gets plugged into to our function.
Okay,
The second one is this concept of, we just have to plug in the endpoints from each other and subtract. Where f is an anti.
wait, so this is a different F?
Yeah, there's two pieces to it. Yeah, so one is completely different from the other. We're saying two different things at the same time.
So where do we derivatives? You know, we have like all those like the power rule, where we have like super easy way to find them. We have the same thing for antiderivative, where you like.
So you just go back.
Yeah.
You just use the same rules as derivatives, you just go backwards.
Yeah, let's see. Let me see where the so they don't give you so on page 392. Once we get to 5.4, then we'll establish a table that gives us all the antiderivative tables.
No, not a table.
Oh,
Are annoying.
Aye. But now what we're going to do is we're going to think back today. We're going to think back to what makes that derivative, and we're going to put it in.
Okay.
So I have to think of both ways here. Okay, so problem number one, it connects the derivative to antiderivative, meaning that those are just antiderivatives of themselves. Part two says I can plug in endpoints and get a value. I get actually a numerical answer. As long as I plug in B and A, and as long as that derivative relationship still holds. Are we good? Okay, let's try some.
And that's the fundamental theorem of calculus.
That is true right there.
So that's what we did in this other, when we were doing the curve thing and when we showed it before, when we had the connection to part one.
Yeah, So we showed the fact that it was an antiderivative, and then part two, we showed the fact I could just plug in the 3 and the 1, and I can get the answer of the area.
We did the example problem with that one, right?
Mhm.
Okay.
Okay, are we good?
Yeah.
Yeah, just want to make sure that it's cohesive and will follow logically here. Okay, so example 1 now, exercise 1 maybe. I want to know, let's do this here. Let's see, remember when we started off in chapter 1, we went from 0? Let me find it. You guys in your notes here, when we just started chapter 1, I think we had something about x squared, didn't we? X squared. I think we went from 0 to 1. Is that right? Can you guys flip back to your, no, sorry, chapter 5, 5.1.
Yeah, I think we did.
Flip back in your notes there. 5.1, it was the example problem we're trying to, 1/3, okay. So let's find this out now that we know this good stuff here. So I go from 0 to 1 of x squared dx, that's my function, right?
Oh, that dx is annoying me.
My,
It looks like the derivative, and I don't know what it is. What is it?
dx over dy.
it's just naming, it's naming the variable that you're using, but dx has,
So it's saying, we're using x.
yes,
Why do we have
It's
to
a tab.
name it?
Yeah, why did we have to name it?
Okay, it's because when we take the antiderivative, this disappears. So you're declaring this to be the derivative of this. This is already a derivative of something.
So it is related to the derivative.
Yeah, that's it. And that's the variable that you're using. So variable you're using, and the fact that that's already in derivative
So
form,
it is the derivative.
because we're gonna take the antiderivative out.
It's the same,
Oh,
it is the
but
same
it's going-
dx.
That's how we would give an
Then
answer.
why didn't
for
you tell us it
derivative.
was before? Okay, so it's saying that that's the derivative and we can go backwards.
To find the antiderivative. Okay, talk to me now, think in your head here, real quick here. if I had this as already the product of a derivative, what should have been the what should have been the thing that we took the derivative of? And so if you want to,
1/3 x.
absolutely, we go there, 1/3 x cubed. We're gonna ignore the c and the positive c for now. We're good? Let's ignore that.
We were doing 1, and then so we put in 1 for x, and it's 1/3.
Say it again.
When we were doing the problem in 5.1, then we were doing it from 0 to 1.
Uh-huh.
Then we plugged in, and here we can plug in 1 for x.
Yes, we did it the long way. The short way is, let's go 1/3 x cubed, evaluated, and again, some textbooks write it like this. Let me just check. I wanted to just check what your textbook said. Okay, yeah, your textbook does this right here. So whichever your textbook draws it like this, like a big bracket going off to the left.
But only one bracket, you don't bracket the other side?
No, it's actually evaluation. It's the evaluation of x cubed, 1/3 x cubed from 0 to 1.
Okay.
And so the way you say it is evaluated at or evaluated from 0 to 1.
So in the, where you wrote it down below, it's really, what we really did was we multiplied by x dx. Or, wait, you could write it as x squared dx equals that.
Yes, correct.
Okay.
Cool. And jumping back, let's see if we get our 1/3. Yeah, we plug in the 1 into here, right? It's cubed. Minus the 0 cubed. And voila. Remember that? That was the right-hand side and then the left-hand side, and we got a 1/3 both ways. What do you guys say? Easier to do it this way?
You know what?
We can go back to the summation formulas if you like.
No thanks.
Okay. Just wondering. Okay. So let's jam. Let's see. Maybe one more thing. How much time? Yeah. Okay, let's do some easy ones and then we'll get into what happens sort of stuff. Okay, example. Are we good there? Example 1. Are we finished? Makes sense? Connected it to 5.1. This is awesome.
It would be nice to hear, like, it said out the relationship between derivative and integral, like what you're actually thinking about, what it actually is doing,
Uh-huh.
because that seems hard to conceptualize.
Mm-hmm.
This is not gonna be done right now, but.
Yeah. Uh-huh. Let me
Just
think
like
about it. Yeah, let me
think
see if I
about
could
how
formulate
the
it.
point relates to the area in words, not formula, because the
Uh-huh.
formula makes sense, and I see
Mhm.
what's happening, but the words of explaining what it is.
Sure. Let's do this real quickly here. Let's do. Yeah, we can probably do it. Let me do this here. Not words yet, but let's do a graph.
You like graphs?
And our favorite website for graphs too. This could be the joke. Of course, be the joke for a long time.
What I don't understand about math is if we have this faster way to do it, why did we learn the slower, tedious way that we're never gonna use?
Because we had to see that it
We
worked.
had to
before
get,
did the
yeah, we had to
tricky-
get to it.
Yeah.
Did we? But we didn't have to.
What if we appreciate, what if we don't believe, what if you just told us, oh yeah, it's taking the Berkeley backwards?
And I would believe it.
I wouldn't believe
No.
it.
I would. I was like, okay, you've taken math. You're the teacher.
Okay, let's do this
Wait,
here.
what did you just?
Oh, wow, this is interesting. Okay.
Oh my goodness.
Let's talk about it again, just to tweak your brain just a little bit, and then we'll go from there. So this is going to be the graph of, let me go down here.
What?
Okay, let's see if this helps here. Oh, too much. Maybe it's too much.
No.
You can see what we just did, though. Say.
Yeah, so,
I'm kind of confused about that dot that's just hanging in the air. And everything else is connecting, and then that one's just like, yep, I'm here.
Where?
So it's,
The one connected to the red, the one connected to the red.
It's not in the air. It's finding the x value or staying on the x.
Well, yeah, it is. It's staying on the other line, but it's not doing
So,
anything.
yeah,
All the other
that's-
ones are doing something.
okay, let's go with purple line right here. Purple line is the function. We're good. The area is given by here, right? And the orange line is the antiderivative function. We're good?
Whoa.
There's an,
Wait,
I
so
guess
what
there
would
would be,
can you
of
overlay
course.
the derivative function on
Yeah,
top of that?
wait.
So we can see what.
Where's the derivative?
Uh-huh.
I guess the derivative's just, I mean, we can do that because it's negative slope, so it'd be,
Mhm.
the derivative actually kind of looks like the antiderivative, but it's not quite the same. Because it's like the.
Wait, can you add in the derivative graph on top of this so we can see what it,
The derivative graph.
Yeah, where's the
yeah, so we
derivative
can see
graph?
what it looks
Yeah.
like compared to the antiderivative graph in the original function.
I do want to screw it up though. That's the
Okay.
other thing. Let me think about it. Let me think about it and put it into words of the relationship. And I could probably do it by Monday here. So, let's see, talk to me here. This graph, confusing or actually making sense?
I think it makes sense.
It makes sense.
It's between the antiderivative, right, and the graph itself though, right? It's not the derivative itself. So it's one more
It's
step
not-
that Sadie's
yeah.
asking. Okay. So let's talk, oh yeah, let me think about it by Monday.
Yeah, I mean, it's fine to use. I'm not confused about that. It's just,
Mhm.
I'd like to see it.
Sure. Absolutely. Let's jam. Okay, exercise 2, let's go with that.
Yes, if we were really math people, then we would be able to see it in a formula.
Mhm.
But
Yeah, well,
it
I'm not a
shouldn't be
math
that we
person.
need words to go between, but we'll ask.
Sure, sure. Let's go with antiderivative from -1 to 2 of x squared. Yeah, let's try an easy one here. X squared minus 2x.
I'm gonna
There's
take
that
math,
idea.
maybe not like calculus 4, but I'm gonna
But
take
don't
math.
you want it? Wait, you only get to doing like 3 objects at like the end of calculus 3, isn't it?
Say again?
Do you get to doing 3D objects at the end of calculus 3 or the beginning of calculus 4?
Calculus 3 is 3D objects.
Okay.
Uh-huh.
Exactly.
And then calculus 4 usually, I'm not sure about quarter
Well,
systems.
Cal Poly has a
Yeah.
funky.
Because it's,
Isn't
I'm
calculus
not sure
4
if
like
calculus 4 would be that or
theoretical?
not.
we don't like theoretical.
Yeah, does have a question or no?
Objects are concrete.
No, sorry.
No, okay, just making sure.
Exactly. I
Okay.
said I'm not gonna take calculus 4.
Yeah, but no, Cal Poly has funny though, because they have 3, calculus 1, 2, and 3 in 1 year. But it's
Wait,
not the
actually?
same, yeah. Instead of maybe 1 and 2,
Oh
you
my
do 1, 2, 3 at
goodness.
Poly, but it's a different, 1 is not the same as the other one. It's about the same material.
I
It's-
don't wanna die.
What if
Okay.
they accelerate
Versus
it?
Cuesta and
All
Cal Poly,
three
is
at
it?
once?
There's-
Versus a
Right, I
semester
wanna
versus
die.
a
Yeah,
quarter.
correct,
So calculus 3 is not necessarily universal quite.
Where it could be a quarter system, because you can't do.
I
half
think it's a
years.
quarter system problem. I
Yeah.
think it is. It's not a semester. So I think Calc 4 in Cal Poly. Let me look that up. That'll be interesting to find out. Yeah.
Calc.
Oh,
No, but they don't have
five.
Calc 5.
No.
They just have Calc 4 and then you go on to other fun stuff.
Then you go on to like
What?
Theoretical things that mean nothing.
No, it's not.
topology.
Oh, topology.
So all yours, guys. Go for it. Exercise 2. I'm going from -1 to 2 of x squared minus 2x. Again, in your brain, you got to think about what is the derivative that makes that. And maybe we can even we can start making rules here. So we already did x squared, right? So as you guys are writing it down, let's see, that would be 1/3 x cubed. So let's see, derivative, if you go from function to derivative, what we do with power rule is we multiply it, is that right? Multiply and then we subtract 1, right? That's cool. Okay, antiderivative, going the other way. Let's go to the exact operation. Let's add exponent. We're good?
Yeah.
And then divide. That works. So I'm going to go x cubed. I'm going to add the exponent and then divide by that exponent. Good there? Will that work? Minus 2 is here. Going to add the exponent, divide by that exponent. And so if you want to, it's just x cubed minus x squared, right? Would x squared make 2x?
Yeah.
Cool, okay. And the evaluation part, all yours. Plug in a 2 into that, plug in a -1. You'll notice that maybe sometimes you want to do it by themselves because there's a whole piece here to it.
So now we can just plug in the,
And now we probably want to use
And
brackets
subtract.
here, yeah, because
Yeah.
we're going to be doing a lot of subtraction. So let's see, 1/3 into there. Was it 8/3?
yeah.
Minus
8/3
4.
minus 4 minus
That'd be a minus in brackets, right? Minus and then plug it in the,
-1/3.
Well, minus, then you have a negative, so it's gonna become.
-1, so it's
Yeah.
plus actually.
Yeah,
But
plus 1/3
9/3
minus 1.
minus 4 plus 1.
I got,
is -3. So it's, oh, 0? Wait, did I do that wrong?
Wait, no. Well,
8/3 minus 1 more third, or
no, minus
plus 1 more
1/3.
third is 9/3, which is 3. And then -4 plus 1 is -3. So it's 9/3 minus 3, which is 0. So the answer is 0.
bummer.
Wait, no, that's what I was saying. It doesn't, that's what I was saying I didn't like, was
You
the
can do it-
fact that
you
you
can do
could
it
have,
In order of the brackets though,
Is this
it goes
2/3?
-3/3 plus 1/3, or no.
Is it right here? I got -4/3 for the first one, is that?
Yeah, that's the way I put it.
No, wait, yeah.
-4/3. And this will be -4/3, right?
yeah,
-3/3.
yeah.
Yeah,
But it's minus -4/3, so it's plus. That's, yeah, it is.
no, I got 0.
Good 0?
Yeah, that's what I did. I
Shucks.
just like, it's because you have that awful negative part when you go underneath the,
Mm-hmm.
wait,
Bummer.
because it's x.
So let's
squared
graph
minus
it.
2x.
Kate's
What
already
does that
graphing
look
it.
like?
Go for it. Graph it, see what it looks like. And see if the area underneath the x-axis is about the same as the area above the x-axis. Let's see.
Where are we graphing
Oops,
the
I was
derivative
wrong.
or the?
The function itself. So x squared minus 2x from -1 to 2.
About even. I don't
About
know.
even? Yeah, I didn't graph it myself here, but let's see if I can.
One's longer and thinner and the other's shorter and
Shorter and
taller.
fatter.
Uh-huh.
Yeah. But the area is not 0.
But one's negative, one's positive, so
But
when you
it
add them
shouldn't-
together, it could be.
But the
exactly
area,
same.
if you're being like, if you're actually thinking about coloring it in, you're not gonna color in 0, you're gonna color in double. You're gonna color in,
But you have to add them together, and since one of the areas is negative, they can't.
you're gonna color in 6.
Is it x squared minus 2x? Is that right?
Yeah.
Okay. Yep, -1.
If you zoom
Is that
in,
right?
you get this.
Okay. Cool. Zoom in.
That makes sense, why it would be 0.
Oh.
See how much room
Boom,
you have?
so
If you can have a
Exact same
negative
this
area,
piece
which is
here,
a little tricky,
uh-huh.
but
And this
My
here.
calculator is so nice.
I actually don't like that area can be negative.
You're gonna get the colors good on you.
Okay, are we good?
I'm not.
So in chapter 5, maybe in chapter 6, we're gonna have to really think through that piece there because you can't have 0 area. It doesn't make sense. There's
I told you
something,
it didn't make sense.
something is wrong here, especially when you're trying to look at the volume of a Coca-Cola bottle,
When you're
right?
thinking about physical things, you can't have 0 area when you actually have area.
Mhm. So we'll figure a way out of it. That's cool. Okay.
Is that?
Next.
in Chapter 6, we're doing that?
Yeah, Next, let's do this here. Let's see, 0 to pi over 2. Hey, this would be cool.
No, sure.
no.
Cosine theta
Oh.
d
no.
theta. How about that?
When it's plot of
Why all at once? No.
d theta. Actually, that's not fun.
So this one, remember, you
Like,
gotta
it
think.
just becomes
Sine
theta.
Okay,
Yeah,
that's
okay.
cool. Okay.
Well,
Sine
we
theta?
shouldn't be too happy
That's
though,
pretty
because this
nice.
is the easy one. I'm sure there'll be one that's really, really, really called?
It's coming.
The trig function problem
wait.
always sucks on the
Cosecant
test.
theta of dx theta or d theta.
No, it's gonna be a long one with fractional exponents.
Oh,
Those ones I hate.
Those are the worst.
And square roots and everything.
All right, you guys talk to me on that.
Then it's just sine pi over 2 minus
What's sine pi over 2? Is it
So this is 90, so that's 0.
square root of 2? Wait, pi over 2?
Sine of 90 is 0, right?
No, sine over 9. Wait.
Sine of 90 is 1.
Oh, sine of pi over 2 is 1. And then. the
Yeah,
sine
and then
of-
cosine of pi
yeah,
of 90 is 0. So it's just 1 minus 0
equals
or
1.
1.
Cosine.
Did we do that right?
I think so, yeah. Did you guys get one?
Yeah.
That is so crazy. Okay, hold on,
It's
let's think back
1
this here.
From pi on to.
So cosine starts off like this, right? And it goes like that? So that means that piece right there has an area of,
So that means the whole hump has an area of 2.
has a whole, say again?
Like that next part, the area is 2.
Oh, right there,
That whole
uh-huh.
thing.
Let's try, let's see. 4, it'll be from pi over 2 to 3 pi over 2, right? Still a cosine though, right? Cosine theta, d theta. Let's do that one. Let's see what happens here. All right, this will be sine theta. Again, 3 pi over 2 to pi over 2. Talk to me here. This would be sine of 3 pi over 2 minus sine of pi over 2.
No, not. And wouldn't that be negative?
I got -2.
Negative
No,
2,
not a
okay.
negative area. That doesn't make any sense at all.
Well, it's just underneath.
Yeah, but that doesn't make sense because areas are positive things.
In physical form,
Just get
yes,
rid of
not the
this.
way we've defined it. That's the thing.
Well,
We
yeah.
have a,
Okay,
we
well
have a
then that's.
definition of,
Do we just end up taking
So we
the
can
absolute
define
value?
it and then,
let's see, sine of 3 pi over 2 is -1,
yeah, we
but we
can say,
subtract.
should we?
Minus
you
one.
Oh,
say
sorry.
take absolute
Do we
value,
tax-
Yeah, you just end up taking the absolute value because you can't
In
have.
real life, you would, but in the.
Correct.
Or we could redefine it and just start from, and just fix it from the very start.
Oh, that's cool. So if you want to go above the x-axis, what we do is we shift it up by another function just so that it stays up there, or we.
Shift it up
Taking
and,
the absolute value.
actually, absolute value, never mind.
So-
That seems a lot easier.
Absolute
Yeah.
value. The only thing is with absolute value, what happens there is, let's say the function that we did before, right? It came down like this right here, right? Like that.
Yeah.
All right, so yeah, we do take absolute value. What's going to happen? It goes like this.
Oh.
So then at that point, yes, you're taking area here, right?
Uh-huh.
And you're taking area here, and you can add it, and everything's fine.
Oh, no.
But notice that it flipped up, right?
I mean, it does make sense, it just doesn't look right.
Uh-huh.
Yeah,
It
that's
looks
weird.
like,
I want to see my calculator graph that now.
But how would it?
I don't know.
How did you get that?
How do you get it to do that?
Yeah,
Or you
this,
could probably
how
just
about,
call them.
that's it right there.
Put an absolute value in the
Uh-huh.
equation. and
then
like-
you're gonna have to figure out how to work with absolute value,
Yeah, you
because
put
you're
an absolute
technically
value.
doing this right here now, right?
My calculator is not, wait, oh, I know. how to
Put a
do it. It's
number.
under
So math,
Math,
and then
number,
and the first
first
one.
one.
The first one?
ABS.
Number.
Oh,
Uh-huh.
absolute value.
Yeah,
Oh, abs. I forgot about abs.
Oh, it does. That's cool.
That's cool. The only problem is, that's how you do it graphically, right? But look to see what we're doing algebraically, or this is what we're doing.
It's so weird.
That's what we're
Yeah.
doing calculus wise. So now you have an absolute value piece in there that you gotta have to think through how to work it.
Well,
So,
Very
Uh,
fun.
that seems
okay.
not something I want to do.
Okay, two more problems. We're on 5.
I think so.
Here's one for you guys. Let's see, there's 6. And how about oh, this will be fun. Dx over x. There we go. That's cool. I like that one.
What's the top number?
Wait,
6.
1, so X.
Say again?
But
Wait,
wouldn't it,
dx over
wouldn't it be X because 1?
X is on the bottom.
Oh, X is on the bottom,
So
okay.
dx divided by x.
So then you'd have to. This is the part that's gonna screw you
Yeah, wait,
over. is
and then
getting
we put
back
another
to
dx afterwards?
No, is that right there?
So
So-
it'd be
Let's write it
equals
nicely.
1 over x times
Yes,
dx.
correct. So Eli's saying it correctly here. It's technically 1 over x is the function. And then dx is the notation and variable. Okay, so think with me here. See what in chapter 3 gave us a 1 over x is the derivative. So what gave us
ln.
that? I like that.
It's funny, we see it in the other direction.
ln
you
of
don't realize
x.
what it is, but it's, yeah.
So
Okay, let's go with it. ln of x is that.
6 minus ln 3. I don't think I want to do that problem.
ln of 6 minus ln of 3. Hey, do you guys know any rules for the subtraction of two log functions?
you do 1 6 minus 3.
Yeah.
Say again?
1
Yeah.
of 6 minus 3.
Hmm,
Is
I
that
know.
1 of 6 over 1 of 3?
Oh, yeah.
oh,
it's-
close. That's the change in base.
If
Almost.
subtraction,
Subtraction. Oh, let's do this here. Subtraction with exponents is the same thing as, or if you divide numbers, you
if you divide
subtract
an exponent, you
exponents.
subtract them.
Yes. Are we good there?
Yeah.
This is the expansion rules and the compression rules for logs. Did you guys do those ever?
6
Yes, we
over-
did.
Okay.
Oh, yeah, we
Algebra
did
two,
those. I just don't
extensively.
remember
Just
them.
one of
We just,
2.
we just
Uh-huh.
forgot everything we ever learned, which is very annoying.
Okay, and tricky one.
Then we can just leave it as ln of 2.
Yeah, ln2 is just fine here.
Tricky
Oh,
one.
of course. Mm, 3 of 1. Okay, I'll give you this one here. Oh, remember your power rule, right? Remember the power rule.
Oh.
This is just a negative x.
Okay, that's cool. We can write it like
Next to
that.
the negative 2.
Okay, so then think about, let's see, what is going to make this as a derivative?
Negative 1.
Mhm, perfect, yeah. What we did, we're gonna add 1 to the exponent
X to the negative 1.
over negative 1. Eli is correct. That'll be what? Negative 1 over x, right? Will that work? Sorry, that's the derivative, right? So we got that on our hands. So we have
Negative 1. X to the negative 1.
you just write x as negative 1, yeah. We could do it that way. We could write it as, it'll be just 1 over x, like that right here, right? Everybody okay with that? So negative 1 to 3, I should put the evaluation bars there. Gonna write it a little differently, guys, just real quick here. This right here gives us, and then into space, because we're just dealing with the number itself. That's kind of what we're thinking about. And then we would actually plug it in because we have to have the evaluation part there. And that's what we want right there.
Wow, that was quick.
Oh, that's cool.
Get it in your left arm.
You missed the best part of class.
We recorded it, so you're doing great. Okay, guys, talk to me. Go for it. What is the answer? And we got a few minutes left. 2/3. Let's see, plugging in a negative, plugging in 3 into here, subtracting off. And I like to put brackets here, just me, because then I know exactly what I plugged in. Negative 1 of that. I'm gonna say negative 1. Is that okay with negative 1? Oh, no, it's a positive 1 because you're plugging in a negative 1 into here, right? So the -1 comes in, it's a negative in here, right? And it's a negative of a negative. Are we good? Okay, +1 there. I get a negative here, I'm subtracting it eventually. So talk to me, what do we have?
+1.
Yeah.
-1
I go with that, -1 1/3 or -4/3, that's fine. Good, except it's wrong.
No.
The answer is correct if you do this here, but our process is totally wrong.
Why?
Why? Because this beard is out there, I give you like 10 seconds.
That's why we just learned how to do it. Isn't it?
Oh, it's, yeah.
Oh.
Where's your discontinuity here?
Yeah.
0, that's right. Did it pass through 0? Yeah, we went from -1 to 3. So not possible. There's a break in our graph. So we have a graph that's going like this.
Infinite area.
Yeah, is it infinite area? I'll let you guys consider that. Is it?
Yeah.
Well, yeah, those are both asymptotes.
Okay, so the fundamental theorem says I can only get value numbers as long as there's no breaks in my graph, and we're done.
I used to get my shot and come back and you guys are trying to break calculus.
Yes, we just broke it.